it's probably going to be here, so we'll go ahead and get started. Hopefully my water keeps me from getting hoarse like I did a couple of sessions ago. But if I do, expect me to take some moments to drink some water to keep me from sounding like I'm literally a COVID patient. So I'm going to avoid too much camera time, if any at all, because as time goes on in this lockdown, my hair is starting to borderline a mullet. So we'll avoid that and focus in on some slides. That being said, again, I try to make sure that these sessions are more about hands-on experience rather than too many slides. So I did my best to keep the slides to a minimum, but we'll try to make sure that when we hit certain sections, we use the slides, of course, to get particular emphasis across. So tonight is definitely going to focus as best we can about aviation weather theory. That being said, of course, we will certainly hit some time in preflight, specifically because that's what most people use. And of course, that's something you're certainly going to need to be proficient in to be able to show what you need to show to the examiner or the prog check pilot, depending on what you're dealing with, whether it's currently a progress check or the actual practical examination. So we'll talk a little bit of theory. We'll certainly try to mix that in with some actual application with aviation weather services. That being said, we are going to look at a flight scenario that I put together yesterday, I believe it was. So we'll use that as our mainstay to kind of give us some progression going forward. I know for most people, weather theory especially is somewhat academic, abstract, boring, uninteresting, or maybe even intimidating. That being said, lots of pilots therefore usually get into aviation weather if they kind of have to pull a lever if they have to move on to the next step. That being said, certainly as we move into positions where we are required to carry a certain responsibility for those that are kind of career track pilots, but even those that are hobbyists, remember that you even have a reduced set of regulations and structure and guidance. So in other words, the onus is even more on you to be able to take all the information in and make good critical decision making. So that comes with the idea that if you have good weather theory knowledge, then you can make good decisions. And specifically, you don't have to make necessarily hard line decisions. What do I mean by that? Meaning specifically that if the weather is looking problematic with gained experience, understanding, and know-how, you can find ways about going about the weather where it's not necessarily just an absolute no-go or a cancellation, but you modify the plan, you adjust the plan to get where you're going safely. So we're definitely going to endeavor into some of that base understanding tonight. We can't hit on every single type of weather scenario, every single type of weather situation. So what we are going to do is focus mainly on one of the big weather producers tonight. And from there, we're going to glean a lot about different types of scenarios and situations that can come about from that weather producer. So that being said, I'm going to try my polling attempt again. Hopefully it works tonight. If it doesn't, then I am just about out of wits with how to make that work. I'll have to get some more help on that. And sure enough, it's not cooperating. So we'll move on. With that being said, just like I said before, we really need to start with the big picture. We need to understand the basic principles that apply when we look at big picture weather. And from there, we can make generalized statements or estimations about what's going to happen in that type of situation. So the more we practice this, the better we get at it. This is not something where we can read a textbook read about different types of big weather pictures, and immediately be able to interpret what's going to happen. You need to practice this. It's not necessarily a different language per se, but it is a certain technique that goes with it. So practicing looking at big picture weather and then comparing that to what actually happens, both forecasted wise, so the forecast that you see in conjunction with big picture weather, but also what actually is observed. So tonight we're going to be taking a look at quite a few documents, because again, this is all about application and building your knowledge. So specifically when we're looking at basics, two fantastic references would be the advisory circular, known as 006B. That's the go-to aviation weather theory handbook that we'll be looking at tonight. And also prognostic charts, as I just said, taking a look at the big picture weather. The more you look at prognostic charts, the more you read them, the better you are at being able to interpret what you expect the weather to do. Again, that doesn't come naturally. It certainly didn't come naturally for me. It took practice. And I even had the added benefit, of course, of being forced to take 2 semesters worth of meteorology. And it still took time for me to get better at this. And I'm still getting better every time I look at them. So again, it's all about practice in that regard. So tonight, we'll start off with simply discussion. This is where the polling was supposed to come in, of course. So lots of pilots can answer the question that we have to answer on the written test, that where does weather come from? And of course, the textbook answer on uneven heating of the Earth's surface passed the test. But what does that really mean, and why do we care? Yes, the sun doesn't heat the Earth evenly, but what that really means, of course, is that we develop large areas of differential temperature. We know this from pole to pole, across from the North Pole to the equator. Clearly, we have significant temperature variations. But what does that really mean? Well, in association with large areas of big temperature differentiations, then you also get sweeping areas of differing pressures. And that's really what it boils down to, is when we have large areas of different pressures, then of course we're going to induce flow, high areas of pressure moving towards low areas of pressure. And we'll get into that specifically here in just a moment when we take a look at the reference. We can see there, Advisory Circular 006B 7-1. That being said, before we do, I just want you guys to have a purpose in the back of your mind. So let's jump to the next slide, that ultimately what we're really looking at tonight, before we get into some academics in the advisory circular, is we're really going to be looking at surface low pressure systems. These are the big weather producers. So if you ever ask the question, which type of systems produce weather, the best answer is the low pressure system. Certainly in the northern hemisphere, with its counterclockwise rotation, it can create lots of different exciting events. And the one that we're looking at tonight is in fact the one that's going to create the weather for us tomorrow by bringing a cold front across. But it's a dynamic system that we deal with. It's one of the big producers of the reason why we see such heavy tornado activity in Tornado Alley this time of year, is the dynamic differences from cold and warm air masses mixing kind of in that Tornado Alley area and developing oftentimes into these low pressure systems. Low pressure systems, of course, are also what turn into hurricanes. They're just very strong, very, very deep low pressure systems. So it's one thing to, of course, we're going to talk about low systems, but we also kind of want to have an idea of generally the consistency that we expect a low system to do as far as track, but also behavior in the United States. A lot of what goes on with the surface low is dictated by what's going on in the mid pressure level altitudes, what's known as the 500 millibar altitude, which is basically half the atmospheric pressure, or just about. And so that's about 18,000 feet. So whatever's going on at 18,000 feet, there could actually be an upper system that helps move that system along, or in fact actually helps strengthen that system. Sometimes there's upper systems that are closed off and create really unpredictable type events where all the modeling completely gets the track of a low or a hurricane off, and the system goes an entirely different direction. We won't get too much into that. The purpose, of course, tonight is to open your eyes into some of this. get you where you need to be for a progress check, help prepare for the end of course practical. But just be aware that ultimately, if you want to know what a low is going to do, if you take a look at what's going on at 18,000 feet and above, that largely will dictate what a low pressure system is going to do. So that's our purpose tonight. So I want you to keep that in the back of your mind now that we jump into specifically the Advisory Circular 006B. So let's switch over to that now. When we look at this docket, we're going to jump straight into chapter chapter 7. But once again, make sure that when you're reviewing these documents, you do take a look at the table of contents so that you have a working knowledge of the document. Because again, you're going to use this to answer questions whenever you have the tip of tongue phenomenon. In other words, you forget something. Well, if you have a working knowledge of the document you're looking at, then of course you're going to be able to pull that information up quickly. So let's jump through this because we've got a lot to cover here. So why am I jumping into wind when we're talking about pressure systems? Well, because of course wind is ultimately affected by the pressure systems, and in association, of course, wind is what will move one type of air mass to another. So most people, of course, even go out on the street and you were to ask someone, where does air flow? Lots of people would answer, of course, that it flows from high to low, like we kind of see depicted to us here. The PGF, we're not going to go too much into detail, but that stands for pressure gradient force. It's a way of us conceptualizing the fact that in this situation, higher pressure, in fact, actually creates a force or induces a force by flow from higher to lower pressure. Lots of people, of course, I'm sure are familiar with what isobars are. These contour lines that you see here are representative basically of that concept of a line of uniform pressure. In other words, the pressure that exists here over the southern portions of, I guess that's Arizona, New Mexico area, would in fact be the same pressure as looks like about Utah, Colorado area. And so the idea, of course, is that when you see more and more isobars of uniform pressure adjacent to each other, then that tells us that, of course, in a short distance, the pressure is rapidly changing. And in conjunction, that tells us that there's a greater pressure gradient force. Now, you would think that a high pressure system, of course, would just flow directly to a low pressure system. But because of Coriolis force, the rotation of the Earth, that doesn't occur. We get a circular pattern that, of course, develops. And most people, of course, are familiar with the idea. You can see this illustration down here below, that if I were to, of course, have that disk stationary and I drew a line across it, I'm going to get a straight line. But if, of course, I begin to spin that disk, the line becomes curved. So this helps us visualize the idea that we're not going to have straight flow when it comes to wind patterns from a high pressure system to a low pressure system. And instead we get circular flow. This may, of course, convey the idea that most people probably are already familiar with, which is the idea, we'll skip ahead to the fact that airflow will flow in a counterclockwise or clockwise rotation. And in fact, pretty much parallel now to the contours instead of directly across them because of Coriolis force, as well as some situations like ground interference known as ground friction that we see here. But just to save some time, I'm going to skip that section. Anyone that's looking at this, highly recommend that you come back and read this. This is the reason why I'm using it once again, instead of just showing you on a fancy slide, is to help encourage the idea that this is where the source of information comes from. Tonight, even if you watch this several times, you're still going to benefit from reading through this section. So that being said, we're laying the groundwork for the idea, of course, of how air is going to flow in relation to a high and a low. Now, why do we care? Well, again, by understanding weather theory, we can glean lots of information that will give us more insight in how to make better decisions from a pre-flight standpoint, certainly, but also in-flight decision making as well. So we're going to focus, of course, on the low, as it's the major low, weather producer. So with that being said, we'll start, of course, with the low in this situation. We can see that by representation of the arrows, low pressure systems, at least in the northern hemisphere, so this is backwards in the southern hemisphere, low pressure systems in the northern hemisphere will rotate airflow counterclockwise. So in this situation, I want you to begin to start to visualize that because of that counterclockwise flow, how is it going to influence different types of air masses, okay? So there are different types of air masses, of course, relative to a low, south of the low pressure system and north of the low pressure system, as well as east and west for that matter. That's really what's going to begin to help induce different types of weather patterns when we talk about a low pressure system that we'll get into here more in just, excuse me, in just a moment. So just as a representation, you can see in a low pressure situation, because of the pressure gradient force, of course, trying to flow from higher pressures as represented by the higher numbers here. Sorry, let me get you a better marking. So higher pressures flowing to lower pressures, we can of course see that pressure gradient force tends to pull in that direction. But when you combine that of course with Coriolis force due to the rotation of the Earth, that's where you begin to see wind flowing parallel to the isobars instead of across them. All right, so that being said, there are circular patterns, or I should say circulation systems that go on across the globe. We're not going to get into those different circulation systems. Do you need to necessarily know these for a private, say, pre-solo cross country? It would obviously benefit. Is it going to dictate terms necessarily for you on a local, 50, 60, 70 mile cross country? Generally, no. But should you know them by the end of course, I would definitely recommend them, and especially recommend that you know them by your commercial. And so an association, certainly CFI applicants need to know these as well. That being said, we're going to focus in on really what these circular patterns do for us where we are geographically. So let's actually jump to the Potts Handbook of Aeronautical Knowledge. Yeah, you can't get away from this book. It's still got more information even pertaining to weather theory. Namely, what I want to hit in on is this ideal, that we actually, in fact, have different air masses that, of course, are going to move into the contiguous United States, and especially this time of year where you have significant differences between these different air masses. That's, of course, where we start to see more dynamic weather in conjunction. So just to go over a couple, you can see, excuse me, this one here. This, of course, represents the continental polar air mass that moves, of course, from Canada down south. It's very dry and, of course, as we would imagine, very cold, whereas you've got the maritime polar over here. The maritime polar, of course, obviously moves in from over the ocean. So it's bringing cold air, yes, but it's also bringing in moisture as well. And the opposite side of things, clearly we have airflow from, say, the maritime tropical. Obviously, that's going to be moist, definitely, but now warm air. And so now we're starting to see some dynamics in this situation where we see different temperatures and in association, different pressures. So we're getting a mixing of air. And like I said, the springtime weather, especially for Tornado Alley, this is particularly the reason why they have such dynamic weather, is because you're having significant differences in temperature and in association pressure when it comes to these air masses. So keep that in the back of your mind, because we're going to see that in action here in just a moment. Let me get some drink of water real quick. All right. So let's jump back into this whole idea of specifically about this low pressure system. Again, if you want to read more, we will make short reference to these pages we already have, but specifically read up in 12-17 to 12-22. But what we're going to now do tonight is we're going to take a look at a specific flight scenario that I made reference to before. In this case, we're going to take a flight from Destin, Florida to Fort Worth, Texas, going to Kilo Foxtrot Whiskey Sierra. And we're specifically not going to focus too much on the flight planning. We'll just use the route for now as direct, more or less. Initially out of Destin, you've got to do a little wiggling for Eglin Air Force Base. But our main focus, of course, is going to be taking a look at a standard weather briefing through ForeFlight. This, again, is to get you familiar with ForeFlight. So we're going to drag our feet a little bit here to make sure that people are familiar with what we're expecting to get briefing-wise with ForeFlight. And then, of course, from there, start to look at the weather situation in conjunction. All right, that being said, remember that especially when you start to deal with dynamic weather situations, if there's even the remotest possibility of the weather becoming unpredictable, or in other words, doing something different from forecast, then you shouldn't just have one plan. You should have, in fact, two plans at a minimum. A plan, of course, for what you expect to happen, and a plan if it does not. Which means, of course, that you also need to have some idea of what could happen if what's forecasted or what you initially expect to happen doesn't happen. What else could happen is something you also want to ask yourself, and therefore have an out. So when you start to see decisions being made where the weather comes closer to your personal minimums, in that situation, that's all the more critical that you have an out, if you will. In other words, a backup plan. So keep that in the back of your mind, because we're going to, of course, be discussing alternative options when it comes to this specific flight plan. So let's jump into ForeFlight, take a look at a flight plan from, again, yesterday. So we're going to be looking at the weather predominantly from yesterday, but that being said, we will actually take a look at this exact same system and what it's done today as well. Okay, so we'll pull up the briefing that I pulled up from yesterday, hopefully. 1 second, my iPad is frozen. I may have to restart here. Come on. Let's just restart. All right, here we go. So the error just means that it can't update because this is an outdated flight plan. So you'll see that at the top, but we'll just do our best to ignore that. We're going to skip temporary flight restrictions since our main focus tonight is, of course, on weather theory. That being said, if it was a significant TFR, remember that could, of course, create a dynamic with the weather where you may find yourself being bottled in trying to avoid airspace and weather at the same time. The closed or unsafe NOTAM, of course, is pertinent if it possibly shuts the airport you're trying to get to down. In this case, we've got an aerodrome NOTAM that the airport is closed to practice low approaches. And then, of course, that is effective for a significant period of time, certainly through May into June. In this case, this is at Destin. So no practice approaches into Destin until June 11th, at least. All right, so let's get into our weather products. Let me start off by saying that clearly the more questions you have about the weather, obviously the more you need to investigate, meaning the more the weather moves to your personal minimums, the more you need to investigate. Specifically, when I say investigate, I'm talking about looking at weather products, talking to other pilots with more experience, discussing possible routes of flight. So the closer those tolerances get, and again, everyone has different tolerances based off of their experience, their knowledge, their background, etc. But the point is everyone has a certain, or should have a certain set of personal minimums. If you don't, you should be working on developing those, especially if you already have your license. Those of you who are student pilots, it's something you should be continuing to think about, such that by the time you take your end of course, you have a set of personal minimums, which we'll get to at the end of tonight. But we're going to see quite a few red flags here to start to say, look, if you're really considering this flight, you're going to have to do some extra legwork to deal with this situation. So the first thing they give us of course, in flight, as well as if you were using 100WX brief, is usually you're going to get a combined text with graphical depiction. The graph depiction, of course, is particularly useful because prior to graphical depictions, all we had was a textual plotting that we had to do ourselves or visualize ourselves. So this is particularly nice. We can see right off the bat that not only does flight alert us of the active time, and then of course from there we can interpret that, but based off my proposed departure time, it will be active as we pass through it. In this case, active from April 22nd, as we can see depicted in the red there at 2030 Zulu to 0124 Zulu. So clearly, we already have a concern on our hands from the get-go. If we scroll down, of course, then we get the plain language depiction. I would recommend you do both because on the progress check, oftentimes we're going to ask you to read the coded version. So the more you have practice comparing what you see in the uncoded and coded versions, then the better off you're going to be reading the coded version, of course. That being said, of course, this is a SIGMET issued by the Aviation Weather Center out of Kansas City, Missouri on the 22nd at 1655 Zulu. A SIGMET C outlook valid. So already what we can see is that this is an outlook, which means it's not an active convective SIGMET. What it tells us is that the outlook, of course, is going to be calling for likely convective SIGMET issuances. After that, they give us, of course, its valid time. So it's valid from 1855 Zulu until 2255 Zulu. Now, for us, in this situation, it's a pretty long flight. We would probably really significantly struggle to do this flight in a 172 nonstop. Not only would it be grueling from a time frame standpoint, especially going east to west against prevailing winds out of the west, meaning a slower ground speed, but fuel definitely would be a concern as well. So our proposed departure time is 12 p.m. Eastern time. So if we do the math, 12 p.m. would equate to a 1600 Zulu departure time. So we'll definitely be looking at flying through this area, as it already told us, based off of the projected time there above, and therefore it's going to be a concern. So bear in mind that we don't just look at the radar, of course. We need to see what's likely going to occur, and it confirms to us that it's going to be active, certainly in time frames between 1855 and 2255. So then it gives us the boundary, which we don't need to worry too much about because, of course, it's already graphically depicted for us above. So we can reference that, of course, to get familiar with it. It gives us boundaries based off of distances and cardinal directions relative to different locations. In this case, we've got, of course, as you can see, just the first point of reference. It starts at 40 miles west-northwest of mid-continent or Dwight D. Eisenhower National, which is in Wichita, Kansas, or ICT. I'm not going to go through the rest, but just that basically, if you imagine it, it's giving you this boundary that we can see. excuse me here. Actually, that's the different boundary. Let's see. Yeah, that won't be the different. We'll come to that one in just a second. But irrespective, let's go on. So we can see it's giving us a concern, of course, that there are convective SIGMET issuances expected. Not an active convective SIGMET, but an expectation that that convective SIGMET will likely occur between those time frames. So already we know we've got a concern for some convective activity in the area. A separate convective SIGMET, either active or possibly an outlook. In this case, sure enough, this is an active convective SIGMET. We can see, of course, it's issued by the same location. Convective SIGMET 62C valid until 1855 Zulu. So it's inside of that outlook we just took a look at. Gives us, of course, a different boundary, as we can see there. And then, of course, it's calling for an area of severe embedded thunderstorms moving from 250 degrees at 45 knots with the tops above 45,000 feet or above flight level 450. Hail to 5 inches and wind gusts to 50 knots possible. So obviously some nasty stuff. And of course, if we can see, it's clearly across that area that we were discussing before. Now, this one, as we can see, is outside of our route of flight. So Is it a big of a deal? Well, it's certainly a red flag. It requires more investigation, as we talked about before. As soon as you start to see things creating some concerns, then it's not necessarily a go or no go absolute. It's more about, well, that means that we're going to have to do more homework, more legwork. Just to save time, since we've got so much to cover, clearly there's more areas to look at and discuss, but we already have what we need, which is that certainly thunderstorms are likely. In this case, there also is, lastly, one more convective segment that is active. And you can see in a line there from the southwest to the northeast, it already gives us a purview into the idea of where the thunderstorms are going. I'm going to already guess that the storms are basically pushing up from northeast of Austin and moving northeast from the southwest to the northeast towards, as you can see, that town called Tyler. And so sure enough, in conjunction, we can see that, of course, they give us a area. They can see that it's 20 miles east-northeast of East Texas Regional Longview, Texas, which is the airport GGG, to 10 miles northwest of CWK, a line of severe embedded thunderstorms, 40 nautical miles wide, moving from the southwest, or 230 degrees at 45 knots with tops above flight level 450. Hail's only 1 inch, big deal, right? Wind gusts to 50 knots possible. So yes, definitely qualifying for severe thunderstorms. Specifically, we can always expect that a severe thunderstorm is going to be qualified anytime we can see surface winds moving beyond 50 knots. So as we can see, gusts at the surface are possible 50 knots. Hail in excess of 1 inch, so pretty much there with the qualifier as well. Clearly an area to be avoided. All right, so moving on. In addition, there's also an Air Met Sierra. Air Met Sierras are released for conditions that are not associated with convective activity. How can that be? Well, because surely this system that we haven't actually seen just yet is creating not just one type of adverse condition, but in fact creating lots of different types of adverse conditions. Plus, we also get the dynamic of the time of day, which we'll get into later. So an Air Met Sierra can be created by this large pressure system, and then of course be encouraged to expand in size and coverage by the time of day. So in other words, early morning or overnight type situations can help induce a widespread area of Air Met conditions. In this case, an Air Met Sierra, of course, is for IFR conditions. So we see the bounded area. Let's take a look specifically what it's calling for. So this Air Met was issued by the same location, Aviation Weather Center out of Kansas City, Missouri, on the 22nd at 1625 Zulu. It is an amendment. So in this case, it's for the Dallas-Fort Worth forecast area, Air Met Sierra. So specifically Fort Worth Center, prepared on the 22nd at 1625. As you can see, yes, an Air Met Sierra again is for IFR conditions. Whoops, sorry. Oh boy. There we go. So Air Met Sierra update 4 for IFR valid until the 22nd at 2100 Zulu. For a lot of you, you might have gone through a progress check where you already asked the different types of weather products and when they're good for, what's their valid time, when is the next update. Why in the world do we need to know all these numbers? Is it just to check off a box? It really isn't. It's that extra bit of information that qualifies your knowledge to make better decisions. If you know when the next one's coming out and you're sitting on the fence, then you know how long you're going to have to wait until that next update is released. You also know that, of course, the further you move away from its valid, from its issue time until its expiry, if you will, or its last valid time, then you know that, of course, it becomes less accurate information. So once again, don't just forget, or I should say, don't forget that you don't just look at products for what they are. You've also got to consider how good they are. Mainly, not only, of course, the forecaster, we can't really predict based off the forecaster, but in this case, how long has it been since this was created? And therefore, how accurate is this information? Just like segments, just like convective segments, I should say, we're going to, of course, see a bounded area described textually. But again, Fortunately for us, we don't have to worry about that too much because we can see that graphically depicted for us as well. So we'll just skip through this paragraph, understanding that, of course, that's basically textually describing that same graphical area there. That what we next need to, of course, know is what are they calling for? So air met Sierras, of course, are often copy and paste, ceiling below 1,000 feet and or visibilities below 3 statute miles in precipitation and mist, meaning those are the weather phenomena that would bring the visibilities down below 3 statute miles. The conditions, as you can see, this is critical. A lot of people will see the conditions stated and then kind of leave it there. What we need to focus on is the fact that not only are they what they are, but also they're calling for the conditions to continue beyond 21 Zulu through 0300 Zulu. Now, these come out every 6 hours. And so we can see that once again, this specific air met Sierra, good grief, is valid until the 22nd at 2100 Zulu. What this is telling us is not only do we expect the conditions to continue through the end of this period, but in fact, it's going to continue beyond it for an additional, 6 hours. So in conjunction, they also give us an outlook. Just to save time, of course, an outlook is moving outside of the time frame for the air met Sierra. And guess what? Same thing. Ceiling below 1,000 feet, visibility below 3 statute miles, precipitation and mist. Conditions continuing beyond through 0300 Zulu, I should say. Once again, just to save some time, bear in mind that you should be comparing these to what you see in the coded version to get comfortable with them. And by the way, it's not just about passing the test. It's not just about taking the written test. It is true that with enough practice, you can actually read the shorthand faster. You're able to glean the information you're looking for and move through things a bit faster than when it's written fully out, like we see above. All right, so next we've got an air met Zulu. Man, so another air met, in this case, an air met Zulu is for icing conditions. Same type of setup. Again, just to save time, we're going to scroll down and take a look. In this case, specifically, this air met Zulu is for icing and freezing levels, valid until that same time frame. So they're coming out at the same time in conjunction with the air met Sierra. And so after we move past the bounded area, which we can definitely see is incorporating our route, we can see moderate ice is being called for, at least moderate ice between flight level 200 and flight level 280. So is that a concern for us? Yes, believe it or not, because even if we're choosing to fly at a much lower altitude, it doesn't mean that A, we won't encounter icing conditions, but also B, clearly there's a possibility that with that widespread of an area, there's a weather system that's creating these conditions, and in associations could still, of course, affect you in different ways down below those altitudes. Specifically, in this case, we can, of course, see that those conditions are still continuing beyond the period and moving not quite as far out as the air met Sierra, but until 0100 Zulu. Notice that, of course, the freezing level ranges between 8,000 feet and 16,500 feet, which means if you were planning to fly even near 8,000 feet, even at 7 or even 6,000 feet, this is more homework for us, meaning we've got to find out specifically along our route of flight what the freezing level is likely to be. Bear in mind, IFR to VFR pilots out there, this, of course, is where there's a bit of a divergence. Yes, VFR pilots, we should definitely care about icing, but we know that generally outside of freezing drizzle or freezing rain, which, of course, is falling super cooled precipitation, as long as we remain in visual conditions, we're not going to pick up ice for all those VFR pilots out there. So stay in visual conditions, and you don't have to worry about ice from that standpoint. For the IFR pilots, this is where you've got to do the extra legwork to see where that freezing level is likely to come about. So notice that I'm pulling out little bits of information this is where I'd be taking notes to say, okay, based off of this means I need to look up extra information. I don't just leave this information where it is. It begins to give me a gauge tool of what I'm going to need to do extra in my planning in relation to, forget just saying outright, okay, yeah, I know that I'm not going to be in these conditions and therefore it's not an issue. Remember that these are forecasts in many cases. Air mets are both observed and forecast basis. So in association, you're going to likely get some variance in the accuracy of these products. So I'm going to be looking at that, right? So let's keep those things in the back of our minds so that we can always think about not only our current plan, but also what we would do if things don't go as planned. Not done yet. Still got more adverse weather products. It's starting to build up to say, man, there's definitely something going on here. And in this case, we've got Air Met Tangos. Of course, Air Met Tangos are for turbulence. Still releases the same time frame as Air Met Zulus and Air Met Sierras. Have the same exact formatting. So just to save time again, we're going to scroll past the information because it's the same release times, same valid times, not the same area, of course. So once again, we see a textually described bounded area, but clearly we can see for this one, it's pretty much the entirety of our route of flight. Okay, so that being said, what is it calling for? Well, Tangos, of course, call for at least moderate turbulence below flight level 180 with conditions, again, continuing beyond the period, moving through to 0300 Zulu. Plus, you can also see that there's a separate advisory for low-level wind shear potential in conjunction. Specifically, I believe that's this one, if I recall from what I recalled before. Yeah, same time frame, 2100. It's beyond 2100 Zulu, moving through 0300 Zulu. So not only do you have an expectation for moderate turbulence, basically the entirety of your cruise, you're going to be experiencing likely moderate, at least moderate turbulence, but also now we have a low-level wind shear potential across generally the same bounded area, with those conditions still being called for through the period. So definitely through our entire route of flight, and definitely at our destination. So let's do some summary so far. We have the potential for thunderstorms. So we have active thunderstorms actually along our route moving from southwest to northeast. We have Air Met Sierra for possible IFR conditions along our route of flight. Icing conditions possible depending on your altitude and your exact route of flight. Moderate or greater turbulence, at least moderate turbulence, basically for our entire route of flight, and the possibility of low-level wind shear at our arrival and our destination. So for a lot of people, this would be an easy no-go, and to be perfectly honest, it really is. However, we're going to talk about different options outside of just the plain no-go, just to simply give us the opportunity to discuss more when it comes to weather theory. So let's break with that, and I just want to talk about one more thing. We can even see that there was an urgent pilot report. So urgent pilot reports are released to us as an adverse condition weather product. In this case, we've got a situation where a aircraft reported some kind of qualifier. Usually that's going to be one of two things. It's going to be severe turbulence or severe icing. In this case, we've got both. So we'll read the undecoded version here at the top, so we can see the location is KOSA, which where in the world is that? Well, we won't go to find where that airport is, but if you look, of course, on the charting given to us by ForeFlight, the I there is the representation of the location of where this observation was made. The observation was made at 1618. Altitude is 26,000 feet. Aircraft type is a B-52. Turbulence observed was severe. Icing observed was severe rime ice, which is an opaque colored ice. And remarks came out of Fort Worth Center from AWC Web. So definitely nasty situation. Was it likely that they were flying through convective weather? Yeah, very likely at that altitude plus those types of conditions simultaneously. That was probably observed while flying through some significant convective activity. No guarantees. Do we care about this? Yes. Once again, if our cruising altitude is 4,500 feet, we still care about this because clearly, again, the conditions in the area are ripe to produce this type of situation, which means that just because we're not at that altitude doesn't mean that we can't encounter some comparable situations. So bear that in mind. Other pilot reports, if you see them at a high altitude, yeah, they may not necessarily be something we would concern ourselves with. But this one, of course, once again, gives us the knowledge that definitely the energy in the atmosphere is ripe to create some circumstances. So let's get to finally, of course, what we really came here for as far as the weather theory goes, which is why is what's happening happening? Well, no surprises, we've got a low pressure system. And not only a low pressure system, but a pretty active one at that. So let's get into some of the specific details about this low pressure system. I'll go back to the slides here to kind of get a blown up version. And we're also going to look at some theory, of course, behind this. So I'll draw into this a bit. So we talked earlier about the fact that low pressure systems cause counterclockwise flow. What is so important about that? You know, yes, there's the question that if you're flying from one side of a low to the other, that you can take advantage on altering your route to catch a tailwind and avoid a headwind. That's absolutely true. But also knowing the counterclockwise flow gives us purview into where we are likely going to see adverse conditions. And you can already, of course, see where those adverse conditions are really happening based off of the radar plot. Now, bear in mind that a surface analysis chart normally actually doesn't have an accompanied radar depiction. So what they've actually done for us to make this all nice for us is these are really two separate products. You have a computer-generated modeling that we see giving us the locations of pressure systems, of isobars, etc. And then what we also get is we get a composite of different radar stations giving us depicted falling precipitation. But in fact, don't be surprised if you look at a different weather product, or I should say a different surface analysis source, and you don't see radar. So those are not one and the same. These are separate products that have basically been laid on top of each other. So without that, we already know, however, where it's likely going to be producing adverse conditions. And the reason why we know this is, once again, coming back to that counterclockwise flow. Before I get into that, let's just talk about some of the bits of information. And just to, you know, this is kind of coarse, but we'll use this so that I can draw on this a bit before I draw out some other details. So for those who are not familiar, let's just go through the different spots or sections of the low pressure system. So obviously the L represents kind of the center of the low, and in conjunction with that, the lowest pressure or the point of circulation. Just like if you were thinking about the eye of a hurricane, it's the mainstay of where all the circulation, of course, rotates around it. Also, we have a warm front depicted here that represents not just a line of warm air, okay? This is a representation of a frontal boundary, a point of contention between two different types of air masses. Generally, because of the counterclockwise flow, we have warm air being drawn in towards the low, but in this case also drawn around the low from the southern section of the U.S., specifically in this case, most importantly, from the Gulf. Remember how we talked about that maritime air mass moving in from the tropicals? That tropical air mass, in fact, of course, is obviously going to be warm and moist. So in this case, specifically, it's drawn from the south to the north. And of course, in conjunction, it's going to be forced into a colder air mass here. So one of the things that I made as a mistake for a long time as a student, and to be honest, well into my commercial and even beyond that, is I never really thought of these lines as just that, a front. What did a front really mean? What it really means is that we have two different air masses. We have an air mass of warm, generally wet air here, and we have an air mass of colder air here. And that warm boundary, of course, represents what's going on at the surface between these two air masses. It's the frontal boundary where these two systems are mixing. Also in the low, you have on the other side a cold front. Well, it's basically the same principle. Now we have cold air being drawn counterclockwise around the low. In other words, northerly latitudes is associated, of course, with generally cooler temperatures. And this can be fed by those cold air masses coming up from Canada and from the Maritime Ocean over the northwestern sections into the Pacific. So we've got this cold air being forced to the south. And so once again, we have another boundary that represents a cold air mass, lots of times generally drier, and we'll expect that to be the case in this situation. You can kind of confirm that based off of the radar. It's coming over a landlocked area where there's not a lot of moisture to feed this air with moisture. But what it is also doing, of course, is it's moving into relatively warmer air. So once again, you get a dynamic also on the cold front side. This dry line symbol represents kind of the same idea, that dry air is being pushed into warm, moist air. And again, if that moist air is lifted because it's being pushed up over a dry line of air, then in conjunction, it could create rain showers and thunderstorms. But generally, especially in this time of year, so in association with the springtime, usually the most dynamic area across this cross-section of the country. That's not necessarily the case in Florida, because in Florida, oftentimes low pressure systems bend to the north as they follow those 18,000-foot winds that we talked about. The winds prevail out of the west, yes, but oftentimes they shift out of the southwest and they push systems into the northeastern sections of the country. We still get weather, but we usually get weather from the cold front or the cold air being pushed down from the north into our area. But for this area, lots of times in this time of year, it's going to be on the eastern and northeastern section of the low where this warm air is being forced northward. And this warm air is always going to be wet, because where is it located? It's the Gulf of Mexico. So you can begin to basically start to predict exactly what's going to happen without a degree in meteorology, without even taking a course, just by some basic understanding of where these systems oftentimes track, and in conjunction, therefore, what they're going to do. The other thing that we see here is these trough lines. And in this case, there's a lot of trough lines. Trough lines, basically what you can think of them as they're lines of elongated low pressure. If you see, what do you see the isobars doing around the trough lines? You see the trough line causes a bend in the isobar. And remember how we talked about airflow? The wind is going to flow parallel to those isobars. So what happens when you've got an area where those bends in the isobars are sharper in conjunction with an elongation of that low pressure? Well, that low pressure line causes, of course, a shift in the wind. In association, the steeper the bend, like this one or this one, the airflow's got to turn around that. And of course, what do we associate with changes in wind direction? We create shear. That shear, of course, can do several different things. It can create not only, of course, just wind shear that most people, all of us are probably familiar with, but also it can create points of contention that can, of course, create convective activity. So sure enough, one of the worst places in this storm is largely along that area where you're getting a large amount of shear and in conjunction a significant amount of convective activity. Clearly an area to avoid, right? So if I was already starting to try to make my decision based off of this present condition, clearly I wouldn't want to come in from a northerly route. It's pretty obvious that we wouldn't do that anyways, coming from Destin, coming from the Panhandle. But start to think, of course, about that. Think about not only, of course, how we can take advantage of a low in regards to the winds, but specifically where are areas that you want to avoid. We already can answer just categorically that an area to avoid is the east and northeast side of a low. Also, what else do we know about lows other than counterclockwise rotation? Well, we know because it's low pressure, the air tends to rise, and in conjunction, of course, lifting action occurs with a low pressure system. So remember, if you recall back to, of course, what does it require of us to create a thunderstorm? We know that we need moisture, so we've got that. We also need instability, where the an air parcel, if we lift it across the atmosphere vertically, it's going to tend to rise because the air is more and more a difference, I guess I should say, try to say, in density. So a molecule lifted from the surface is less and less dense than the air above it, it's going to continue to rise. And the main contributor to that idea is temperature. So if you looked at different altitudes, the more drastic the temperature cools as you go up in altitude, the more unstable the atmosphere is. Well, guess what we're going to get in this situation? We're going to get just that, because we're mixing warm and wet air. So the actual condition of the low pressure system creates instability, and it pulls moisture in. The last thing, of course, we need is an initial lifting action, which can be created in a multitude of ways. It can be created by the warm air being drawn from the south to the north. It can be created by the, sorry, that's inappropriate. Let me draw the color code. Some cold air forcing warm air above it. And then the low pressure system itself creates this lifting action as well with its low pressure situation. So another place to avoid is moving closer and closer to the low. Generally, even outside of convective activity, if you were just talking about trying to stay above cloud tops, the cloud tops are going to trend to be higher and higher altitude-wise as you move closer to the low, outside of convective activity on its own. Okay, I think we've dealt that a good blow, so let's move on back to the slides. Let me get a drink of water before we continue on. Okay, so I tried to draw some arrows there, but bear in mind that one of the complications that these things often have is that they're just a single shot. And so once again, another thing that I also oftentimes struggled with was with visualizing what's going to be happening with flow, but also in conjunction with flow, what's going to be happening with the thunderstorms. So I want to visualize, now that I expect, based off of the forecast, that there's a likelihood that thunderstorms are going to occur, where are those thunderstorms going to be coming from? Lots of us probably are fairly comfortable with using a terminal aerodrome forecast. It's kind of the mainstay of getting an idea forecast-wise what conditions are likely to be at in different locations. But there's a lot of shortcoming with forecasts when it comes to the terminal aerodrome forecast. The quality can depend on the meteorologist. All you have to do is hang out at the flight school to hear enough of the school's opinion on the quality of terminal aerodrome forecast. But even a good terminal aerodrome forecast has a limitation. Can you visualize what's going to happen? Can you actually see the clouds move in? If it calls for thunderstorms, can you visualize what kind of thunderstorms those are going to be? Can you visualize what direction they're going to come from? Can you visualize which direction they're going to move to? And of course, in association, not all thunderstorms are created equal. So one of the things you really want to practice at is visualizing the progression of things. And there are tools out there that, of course, can significantly help us with this. So this is actually that same low pressure system today. Those winds have caused it to begin to pull to the north. And in association, not only do we now have a cold front and a warm front in conjunction with this low pressure system, but that cold front's moving faster than the warm front. And so we now actually have an occluded front, which is depicted in purple right there. And you kind of see the adjoining triangle and half moon shapes representing an occluded front. So this low pressure system is kind of creating all types of situations. We'll talk about what we expect condition-wise associated with the warm front. Not always, but sometimes a warm front will certainly produce widespread IFR stable conditions. We've talked about the fact that a cold front can certainly produce more convective, significantly fast-moving cold fronts, especially dynamic convective activity, as we're expecting to see tomorrow. And then in an occluded front, where the occluded front is located, you kind of get both. You possibly get both types of circumstances where you can get widespread IFR conditions, low ceilings, low visibilities, but also convective activity as well. And especially in the winter months, it's a good place to possibly see freezing rain. That being said, you can see freezing rain or freezing drizzle in any of these three types of situations. But what we do see now is that low pressure system bends to the north. Mainly what Florida is going to be affected by would be the cold front. All right, so this is what's happening now. Let's kind of compare what we can actually see visually. So this is earlier today. I hope this comes out pretty smooth for you guys. If you're on an iPad, it's probably a little choppy. But let's talk about a couple of things here. First of all, where in the world is the low pressure system located? Well, if you really start to pay attention, up in the northern sections, you can actually see some clockwise flow right here. Make sure my laser pointer is actually popping up. So we've got counterclockwise flow here. So the low pressure system is situated over northern Arkansas, southern Missouri. And in conjunction with that, we can see literally some of the things that we talked about earlier happening. We can see the moist air being drawn in from the south, but specifically in this case, this is largely the convective activity. These are these lines of thunderstorms and heavy cloud coverage. Why in the world are they moving on a southwest to northeast bend though? Well, it's largely dictated by that cold front. So if we go back to the previous image, again, where is flow happening in this situation? Well, the airflow is not only flowing in towards the low and counterclockwise, but in this case, it's going to flow along and in front of the cold front boundary. So airflow is moving towards the cold front, kind of like this, but it's also flowing across the cold front, generally in towards the low pressure system. The high pressure generally behind that cold front, which is basically a line of extended low pressure, which we'll actually graphically or see depicted here back in the advisory circular, is going to be drawing in towards that cold front. So pushing out towards that cold front boundary. Of course, that air being cold itself, but dry, as we'll see depicted on our satellite imagery here in just a second. So again, back to this image, we can see the low pressure system circulating here to the north, drawing these lines and these bands of thunderstorms from the southwest to the northeast. Generally, the airflow therefore is going to feed in. You can see right here, look at the clouds developing over the Gulf and being drawn from the south to the north, drawing that moisture in towards the system. So what do we know categorically to be the case? When you're dealing with a cold front like we're going to be dealing with here tomorrow, the thunderstorms aren't going to flow just straight east to west, even if the low pressure system was flowing straight east to west. What we're oftentimes going to see is the thunderstorms are going to flow in a southwest to northeast pattern. So it's one thing, again, to look at the TAP and say, okay, the thunderstorms are going to be in the vicinity at 3 o'clock, and they're calling for 2 miles of visibility and heavy rain at 4 o'clock, and then thunderstorms in the vicinity again an hour later. But now we can actually see what's going to happen. We're going to see those thunderstorms move in from the southwest and move to the northeast. So you already have a predictive power on saying, okay, how are we going to modify our route relative to that? Okay, so this is an added benefit of visualizing the flow happening in this type of situation. Now, to kind of further give us glimpses into what's the weather's going to be doing actually at the surface as far as the wind flow goes, again, we're going to go one more time back to Advisory Circular 006B and take a look at the flow in relation to a pressure system. So let's go back there. This time, I don't know what I'm looking for. So once again, let's do a little bit of legwork together and go to the table of contents. And what we're looking for, of course, is some type of descriptor in relationship to fronts, right? Because that's what we're talking about. So we can see that they get into things like earth, atmospheric heat imbalances. Before that, we've got water vapor, the hydrologic cycle that we'll get into a little bit later, atmospheric pressure, weather charts, wind, global circulations, jet streams, chapter 10, air masses, fronts, wave cyclone. So we'll go here, and then we're going to jump ahead a couple pages to what I want to look at specifically. So here is what's actually happening wind-wise relative to a cold front. Now, I did show this on the first aviation weather seminar that I talked about before, but now we can kind of see from what we first saw satellite-wise, a top-down view, in addition to this idea that, again, you can see that warm air is being drawn in towards that low pressure extended line off, in this case depicted to us as the cold front. And of course, because of that, as it's drawn towards the colder air, when they meet, the warm air, of course, being less dense, is forced aloft. It's going to clearly be moist, as we know in this situation, because it's located over the Gulf. And so in association, it's going to lift into convective activity. So think about also the fact that as this cold front is not only kind of an elliptical shape, but it also is fast moving. And that's really one of the key takeaways, is the fast moving systems don't allow for homogeneous conditions. Now, what do I mean by that? Well, the less like this air mass is to this air mass, the more dynamic the weather is going to be. A slow moving system allows them to mix more and therefore become more alike each other, and in association, less dynamic weather. So a key takeaway is fast moving cold fronts create dynamic weather. Oftentimes they're very shallow lines of weather as well, if they're isolated. Why are we seeing such widespread conditions, however, say for example on the GOES satellite image we just looked at? And the reason why is because we're dealing not with just a cold front, we're dealing with a massive system of both a cold front creating conditions, a warm front creating conditions, and then the low pressure system itself. As that low pressure system pulls away from us, tomorrow it's very possible, depending on how fast this cold front moves, that in association we get more of a thinner, I should say, line of band of thunderstorms rather than just a continuous mass of thunderstorms flowing in and out through the entirety of the day. But that's going to depend on several things. So this finally comes back to one of the key takeaways. Everyone's, of course, going to practice looking at prognostic charts, looking at forecast charts. But remember that these are forecast models, and therefore in association, there are inaccuracies. So they can get things wrong. In fact, talking with actual meteorologists, a lot of times they will say that one of the hardest things to get right is the passage of a frontal system, meaning it's very difficult for them to get just right how fast that system is going to move. You've probably seen it yourself where a cold front's forecast to move through our area, it slows down and becomes stationary over the panhandle. Happens all the time, where the forecast is just completely different from what actually ends up happening. Which of course brings us back to the idea, as I talked about before, that you're going to have a plan of action based off what's expected to happen and a plan of action based off of what may actually happen. Okay, so let's go back to our route of flight and now get a little bit into some decision making in response to this. So let's go back to our briefing and take a look, first of all, condition-wise. Yes, again, a no-go option is clearly an obvious option, not going at all. But let's start to investigate a couple of alternative options where we are going to go, but clearly we're going to change our plan. So if we were in Destin, we obviously could wait, right? That's probably the easiest answer. And in other words, wait until the system pulls clear of our area. Well, let's just take a look at an example. So this was planned yesterday afternoon. Let's look, first of all, just foremost at the thunderstorm activity. So has the thunderstorm activity cleared the area by now of Destin? It looks like it just has. So clearly that's an option, right? So we've delayed 36 hours. If we were up for a night flight, it looks like a night flight might be viable, at least as far as convective activity goes. You could still, of course, have concerns in relationship to IFR conditions or other types of situations, turbulence, etc. What about not waiting? If we're going to leave the day of, what are alternate options? Well, right here, just from a get-go, I can already see that, of course, just from a VFR standpoint, at least based off what's currently observed, I could investigate an option and perhaps going until the conditions deteriorate, right? So fly up to an area where the conditions deteriorate and wait there. Now, why is that perhaps a better option than just waiting it out in destined? Well, it comes back to what we expect to occur consistently with these types of systems, especially this time of year. We know in the United States, at least, not across the world, but in the United States, you have prevailing westerly winds. So the flow is going to prevail out of the west. We can confirm that. Generally here's the winds at, say, 9,000 feet. So you can see the low pressure system is affecting some of the flow. So it's not straight out of the west, depending on where we're looking, because of course you can see that the low pressure system is affecting this area. You can kind of even pinpoint where the low pressure system is located. It's moving up into Kentucky now, up through Nashville area. But generally outside of that, yes, the winds are prevailing out of the west. So if you're trying to go from east to west, to fly from here to, for example, Texas, you know you're going to be dealing with a system that isn't going to just move out of your way. It's not going to, in other words, cross your flight path from the south to the north oftentimes. Oftentimes it's going to move with the prevailing winds down from the northwest, across landlocked areas, and then as it draws in that warm, wet air from the Gulf, it's going to start creating havoc. And so in association, we're going to have to wait if we're trying to fly across that area. So one of the things that saves us time is, of course, flying up to where the conditions obviously deteriorate, and then in conjunction, wait it out there, which saves us time, because waiting in Destin, it takes 36 hours of waiting. Waiting in Louisiana, you may literally save a half day or more. Now, is that an option? Well, again, comes back to the idea that if a no-go is not necessarily what we're going to at least choose at this point, the answer is we don't know. We're going to have to do further investigation. Time-wise, we won't peel into that too much, except to say, not only, of course, would you need to look at observations, right? So as we scroll down through these categories, I can see green, which of course represents a categorical VFR condition. We can see that right about the time we cross past KESF along our route of flight, it's presently broken at 11,000 feet. And then now KIER, you're getting thunderstorms and rain in the thunderstorms of light rain in the vicinity. The clouds, of course, are lower at a scatter layer at 3,500 feet. And they're also reporting lightning distant all quadrants. So this starts to give me an idea, of course, of where you may possibly get. But again, even then, this depends on how soon you leave and how soon this system pushes these conditions further on, which requires further investigation on our part. So you may end up finding that, of course, based off of observations in comparison to forecast, you end up getting closer to maybe somewhere further along to the east on the maybe eastern border between Louisiana and Alabama. However, is a direct route your only option? Clearly it's not, right? So let's look at the conditions that this system is going to create and where we likely expect things to be better. So this, of course, is what's currently occurring. We're going to go back to what we expected to occur yesterday. So let me bring that back up just a little bit. We know that the low pressure system is going to track generally on a east-northeast line initially and then curve further towards the north. So in other words, as we talked about before, a northerly route would not be the best option, which means the opposite. The southerly route would be a better option. So from a VFR standpoint, we could certainly consider the option of choosing to fly more a southerly route, in this case, more along the coastline. Could you do this IFR as well? Absolutely. You're generally going to expect better conditions along the coast, but it also boils down to, of course, are you going to get that if you file IFR a southerly route? And the answer is it largely depends on the situation and the circumstances. But certainly VFR, we could expect it outside of complications with airspace, we could get a southerly route. And in conjunction with that, we know that based off of what we see, so let's just modify a route to say maybe we're going to choose to end up actually flying through Gulfport, Mississippi, and through New Orleans and staying on the southerly route, and then actually coming in, trying to fly around, of course, the conditions along the south sections, more along the coast, into Fort Worth once we clear the worst parts of it, somewhere around Houston. Why? Now, this seems kind of obvious and elementary, but why does this work specifically in this situation? It's relative to the fact that the low pressure system is where it's located. Now, does that mean that there wouldn't be any cloud cover? Well, this prognostic chart's not going to tell you that. That's where, of course, we would need to do a further investigation of terminal aerodrome forecasts and compare that with METARs to see both what's an observed ceiling as well as what's actually forecasted. And you really want to pay attention to consistency. In other words, don't just look at each one of them individually, but you do want to start to glean the idea, is there a consistent layer across the area? If not, and it's more varied, then of course you can expect more dynamic conditions. So just as an example, let's take a look at more of the southerly airports just initially and see what they give us. So as we move into Mississippi and Alabama, along the coast there, past Pensacola, we're seeing few at 3,000, we're seeing clear, we're seeing clear, we're seeing few at 7,000, few at 6,000. Certainly, at least initially, it's a good sign that a southerly route along the coast is a better option relative to this system. As we continue along, it still remains clear past Gulfport. So definitely by the time at least that we get into the Louisiana area, we're looking pretty good as far as conditions go. We're still seeing clear conditions up through that area, even as we move further inland. So you would have an expectation that if it's clear inland, then at least in conjunction with this system, it's probably clear along the coast as well. So these are a couple of additional options other than just a no-go, is to alter your route clearly, but alter your route not just randomly, but in relation to what you know theory-wise in conjunction with this system. Specifically, we know that the system is going to stay to our north. Yes, it is going to draw moisture in from over the Gulf, but that isn't initially going to lead immediately to convective activity necessarily. Now, that being said, you may be saying to yourself, well, I see that, but then I still see convective activity even as the low is well to our north and drawn across, in this case, Destin itself from the Gulf. That absolutely can be the case. But you also see that these systems aren't as widespread as conditions are further to the north. For example, just looking at the radar return from the edge of that precipitation bend to that precipitation bend is about 35 miles. So you possibly could have enough spacing between cell to cell that you could fly in between them, no problem with enough separation. Specifically, of course, we're looking for about 40 miles of separation between severe thunderstorms. This precipitation return is not severe. This one is pretty nasty and certainly would warrant some effort to avoid. You also may be asking yourself, by the way, well, what about that precipitation in between? It's still falling rain. It is. Unfortunately, what these radar returns don't tell us is what altitude that's at. Lots of times that could be high altitude blowout. If I reduce it to the lowest tilt, it looks like it may still be possibly falling at the surface. It's difficult to say, but you can see it kind of cleaned up a little bit as we lowered the tilt angle of the radar. So is this a go? Is this a no-go? Well, we're looking at newer radar images opposed to what we proposed before. So this isn't an absolute. These are just some of the considerations that each of us should take when it comes to, if it's not immediately a no-go, what are my alternate options and how is that going to work out for me? As we said, we make a plan based off of what's going to happen. What if things, of course, don't work out for us? Well, clearly, if we're taking a southerly route, another added advantage to us is, guess what? Lots of people like to live along the coast, which means more airports to divert to. So by taking a southerly route, not only are we advantaged weather-wise based off of this weather system, By the way, if this low pressure system was in the Gulf, this would not be a place you'd want to be, right? Because that positions us on the east and northeast side. So it's all relevant to the circumstances. This low pressure system, as we know, is to our north along this route, and so it's a better option. It would not be the same situation if the low pressure system so happened to take a southerly route across the Gulf Coast. So not only are we advantaged, at least in this situation, with weather, but we're also advantaged from a diversion standpoint because there's plenty of options when it comes to that. We're pretty spoiled here in Florida. When you move out west, for example, you're not going to have nearly as many options when it comes to a diversion. So here's Western Texas, right? So you've got El Paso, and the next nearest airport is 50 or 60 miles away, and it's a small non-towered airport. So bear that in mind, that even route choice, of course, gives you options when it comes to a weather situation that's pushing your own personal minimums when it comes to, of course, diversion or alternate options. All right, not going to keep you all here for too much longer, so let's move through these slides. So let's go back to those slides so we can talk about a couple of other things in comparison. This is the video of the GOES satellite now on the back side of the system. And what do we see? We see dry air. So that cold air, of course, you still kind of see by the clouds that temporarily formed over the center of Texas and then dissipated as the sun came up. They were still a good visual identifier of what the wind flow is doing, right? It's moving in behind the cold front lines. So that high pressure is going to be drawn in towards the cold pressure on the backside. What does this tell us specifically about wind prediction? Well, you know that the wind is going to be flowing to the cold front as it approaches, and then the wind's going to be flowing to the cold front after it passes. So tomorrow, you can already predict the winds based off of where the cold front's going to be relative to us. And that tells you, of course, what you're going to be dealing with as far as situations go when it comes to choice of runways, relevant to, of course, minimizing crosswind, maximizing headwind. But we also know that after a cold front passage, we're going to have clear conditions, but still possibly windy conditions. So this is the expectation you're always going to have now that we understand the dynamic between high pressure systems and low pressure systems. All right. What about thunderstorms themselves? How do we take some of the mystique away from thunderstorms when we can't really practice flying around them or near them or anything like that? Obviously, most people, if you saw this outside the front window, you'd probably be turning around, and for good reason. Admittedly, this is actually just the initial convective activity leading into embedded thunderstorms, not necessarily thunderstorms themselves. But one thing that we really need to be aware of course, is the fact that one thunderstorm is not equal to another. So I had made reference to an advisory circular 0024, 00-24, which is an advisory circular that's useful for kind of getting further purview into thunderstorms themselves. Tomorrow, the thunderstorms that we're going to deal with, of course, are frontal-related thunderstorms. But in the summer, we oftentimes have conditions that are produced that are related to what we call an air mass thunderstorm. And those thunderstorms, of course, are going to behave differently than the thunderstorms that we will see tomorrow. Why is that? Well, it obviously comes down to how they're produced. So before we go any further, I just want to show you that advisory circular to show you a couple of things that, of course, you can get familiar with. Specifically, we get into a discussion, of course, on what types of thunderstorms there are when we relate to maybe a radar image or even just maybe even a satellite depiction. So let's go to that advisory circular. You can actually pull this up in preflight, I believe. And this again is AC00-24 and C is the latest update. So there are, in fact, like I said, different types of thunderstorms. There's single cell thunderstorms. These are your common summer afternoon Florida thunderstorms. They develop, of course, because of the humidity and the lifting action developed by the diurnal heating or the day heating of the earth that causes air to heat up and rise. And obviously that air is going to be wet in Florida. and we kind of get a symmetrical single cell. It doesn't move very fast. They're circumnavigable because they're fairly small in size as far as their lateral coverage. I won't say that they're small like overall. I mean, these things are still very large, but they are definitely circumnavigable with an airplane. They can still produce nasty conditions, but they generally don't last very long because of the symmetry of the precipitation specifically. What do I mean by that? Well, really what we're talking about when we talk about symmetry with precipitation, we're talking about, let me just draw a real elementary picture here for you. We're talking about the idea that when you see the different gradients, and so we start off with kind of a green color that represents light to moderate precipitation, and then it kind of quickly over a short distance moves to moderate to heavy precipitation. We've got heavy precipitation here, and then we get into what's known as the 50 dBz or greater precipitation return. Yes, it's not a perfect drawing, and they won't be truly symmetrical, but it is circular in its pattern. And what this means is, if we look at this from a profile view, is the thunderstorm's going to struggle to survive on its own, because in the thunderstorm, you're getting a rain shaft that creates downdrafts, and it basically kills itself off, because in order for a thunderstorm to continue, it needs updrafts. But the problem is the updrafts are actually being beaten down and dissipated by the downdrafts associated with the heavy rainfall. So these systems oftentimes don't move very fast. They can move 2 to 3 knots. Sometimes they're even stationary. They certainly don't usually move any faster than about 10 to 15 knots. And like I said, because of their symmetry, they don't last very long. Half hour when they get into their mature stage where the rain is falling at the surface. So this is not the case necessarily, of course, with an asymmetrical precipitation return, where now the rainfall is falling on a different section of the thunderstorm outside of where those updrafts are occurring. You may call it a thunderstorm leaning on its side. And so you have your rain shaft here, and you have your feeding system here, and it can continue. These are the types of systems that we see more associated with frontal-based systems. Thunderstorm clusters sometimes we may see tomorrow, but more than likely we are going to see a squall line, which, as you can see, is depicted as, or described as, a narrow band of active thunderstorms, not one thunderstorm, but multiple thunderstorms that often form a line that is uncircumnavigable, unless you're willing to fly 500 miles around it. And of course, these are developed in association, as we can see, with the cold front system, specifically fast-moving cold fronts in conjunction. There's also something known as a supercell. Supercell is a really long-lived thunderstorm. These are the types of thunderstorms we're talking about that aren't a line of thunderstorms, but move quickly through Tornado Alley. These are the things that produce our tornadoes that create such significant devastation. I actually grew up in Fort Worth, Texas, where this time of year, especially in May, we have the notorious, easily golf ball size hail, try more baseball to softball size hail falling from these type of supercells. How can we tell the difference between a supercell and a single cell? Well, that's where, of course, you can take advantage of the meteorologists out there, but also even getting familiar with radar images. That's not something we're going to do tonight. We will kind of maybe entertain the idea of doing a shorter session some night about looking at radar imagery and being able to glean what one radar image return means as opposed to another. But for now, the key takeaway is you don't treat all thunderstorms the same. And so your decision making, your flight planning, your route choice is going to be relevant to what type of thunderstorms you expect. Let's talk about a couple of situations in conjunction here in Florida, just in the summer months. So oftentimes, as I said, in the summer months here in Florida, we just really deal with air mass thunderstorms. As you watch literally across the state, you'll start to see pop-ups, kind of just little circles of precipitation begin to return. So let's just draw that representatively initially. So we start to see here and there, just little pockets that fill in. And this can happen just about anywhere that there's enough lifting action and enough moisture that it can literally be quite sporadic. And that's what, of course, an air mass thunderstorm is. Again, the earth heats up. We're getting moisture, obviously, from the humid conditions, and we're certainly getting instability because of the heating action, but also in association, a lifting action from the heated air. So this is something that is lots of times manageable in Florida. You can fly around these systems with small deviations in your route, unlike what you would be dealing with here, where you may have to make a more significant deviation in your route. We also know that they're short-lived, so they're not going to last long. So even if you're unlucky that that cell moves in over the top of your airport, maybe your destination is Vero Beach, for example. That's a bad example. We're not supposed to go there, so we'll go to Treasure Coast. No, let's do Okeechobee. So our destination's Okeechobee, and a thunderstorm, we're unfortunate to have it move over the airport. We know that with plenty of fuel reserve, we could actually wait it out and expect it to move well clear and land really no problem. Not an issue in Florida. However, we don't actually deal with just air mass thunderstorms. So even outside of large frontal systems depicted on charts, i.e., even if we look at our Prog chart and an afternoon here in Florida, we don't see anything. There's no big weather picture systems, unlike what we see approaching with the cold front there. We're just seeing nothing but just some isobars across the area. Can we still get frontal created thunderstorms? And the answer is absolutely, because of the sea breeze phenomena that we have on both sides of the coast of Florida. Everyone, of course, has been to the beach and noticed that, of course, the wind is blowing quite significantly, even on the the nicest of days, inland from the ocean. And of course, that's because of the temperate and therefore pressure difference that's occurring between the water and the land. So if you think about it, the land, of course, heats up much more rapidly than the water does with the same amount of heating from the sun. So with that diurnal heating, the earth, of course, heats up and we get rising air that lifts, of course, aloft. And in conjunction, obviously, nature abhors the vacuum, so that low pressure created by the vertically evacuating air has to be replaced by more dense air, in this case, dense air from the ocean. And so that creates, of course, a sea breeze. And this happens on both coasts. Now, based off of lots of parameters that we're not going to go into, on one day or the other, one breeze will be more dynamic or more powerful than the other. And so that system will actually continue to spread inland. And guess what? What we really end up doing is we create a frontal boundary of differential pressure and temperature situations. So that in this situation, even on a big picture weather type situation, we can still find ourselves dealing with a line of thunderstorms that spread from east to west or west to east. And this can literally change from day to day based off of the circumstances. It obviously doesn't happen every day. We can have air mass thunderstorms, but we can also have frontal related thunderstorms when it comes to east coast sea breezes or west coast sea breezes. The point being is, once again, you need to stop and think about what you're seeing forecasted. Also pay attention to these products that you can pull out of ForeFlight called the forecast discussion. Lots of times the forecaster will make reference to which coastal sea breeze is going to win out that day in a summer day, and therefore you have an idea of which way the thunderstorms will be coming from and whether it's going to be a line or not. This is a great tool, of course, to develop an insight, not again just depending on when the TAF calls for thunderstorms, but now you can see not only where they're going to come from and where they're going to go to, but whether it's going to be a single isolated thunderstorm or if it's going to develop in a line in association. There's also some particularly useful products now that they've incorporated in a standard weather briefing that help us with this as well. So just to point reference back to them, let's go back here and pull up the briefing one more time and jump ahead to our forecast section and take a look at this here. So as we can see, based off of the depiction here in the southeast, as we see that frontal system approaching from the west, you're getting these symbols with the lightning bolts. Different color symbols represent different coverages. Specifically, if we zoom in on the bottom, you can see T-storms will either be isolated with 10 to 20% coverage, that would be circumnavigable, scattered at 30 to 50% coverage, that would be more like you really got to find an area where you're clear of them, to numerous, which is 60 to 100%, and obviously that's a situation where they're not circumnavigable. And guess what? Right along the coast, they go from an isolated coverage to scattered to, of course, further inland. By the time you get halfway up Louisiana, it's now, of course, pretty much continuous coverage, which this, by the way, further is one of the other additional tools that would help me argue that flying a coastal route would help me avoid this area in that type of situation we're talking about before. This will also, of course, be depicted to us over on a summer day in Florida. So pay attention to these, because this is another way to glean. Yes, there's going to be thunderstorms according to the TAF, but what does that mean? Are they going to be numerous, or are they going to be isolated and therefore you can fly around them? All right, let's move on. I'll promise to have you guys out of here by 9. So once again, just like we talked about visualizing systems and where the flow is going to move in conjunction with that, we can also visualize the flow of storms and therefore determine our routes. And once again, also choose our route relevant to perhaps even if something doesn't happen as predicted. Guess what? In Florida, one of the best places to fly in a summer day is along the coast. Lots of airports, and you're flying away from where that sea breeze system is likely to move storms. That being said, if you fly too late in the day, the west coast sea breeze may literally push the thunderstorms in along the east coast, and you may find yourself trying to avoid those coming from the west. So don't think of it just about what's going to happen, but think about what's going to happen relevant to the time of day as well. So think about that in addition to the flow that's going to occur also. Okay, so just a reiteration, remember, when you're making your plans, it's going to vary, of course, based off the circumstances, and you need to consider time frame relevant to that. So if you're going to fly in the middle of the day and you know that there's going to be active thunderstorms, flying along the coast may be one of your best options. But in association, if you're delayed, you may find yourself dealing with thunderstorms moving off the coast and therefore along your route of flight. Once again, consider your alternates in regards to that possibility, for example. Again, don't just depend on the task. Visualize what's going to happen, not just when it's going to happen. Another further point, of course, to avoid dependency on a wait and see approach, what I call the radar dependent pilot, which is literally a pilot who just makes their decisions based off the current radar. Make sure you're creating your plan, again, based off of what's likely to occur, and again, a plan if it's not. So this gets us away from, again, like what kind of referred to a couple of sessions ago, a reactive pilot as opposed to a proactive pilot. So reacting to the radar because it's kind of the easiest tool to use, as opposed to proactively planning your flight out based off of your knowledge of weather theory and what's likely to occur based off the circumstances. Just a reiteration again, I want to put this into your minds. If you have further understanding when it comes to theory and some of the weather products that we've talked about tonight, it creates more flexibility. This is how, for some of you right now that feel like, man, how do you go from just no-go about everything into a situation where the weather isn't perfect, and yet I do feel comfortable enough in this situation, even VFR. You don't have to be flying IFR to be able to deal with this. The answer is knowledge and, of course, some experience in conjunction with that. That develops your flexibility where you have the understanding to say, okay, I expect this to occur, therefore these are my additional options other than just an absolute no-go. When in doubt, obviously a no-go is still the best option. Last thing I want to talk about is, of course, the fact that these low-pressure systems produce warm fronts. And in conjunction, they obviously can produce fog and low ceilings, which clearly play the biggest role in VFR flight into IMC. So warm fronts, of course, create widespread conditions lots of times. These conditions can, in fact, be hundreds of miles, if not at least 100 miles, away from where we see the warm front depicted on the chart. So what oftentimes happens is as you're flying along, initially the conditions are marginal or maybe slightly better. And so I want to take this moment to say to you that marginal conditions are probably more dangerous than IFR conditions. So, and what do I mean by that? Well, I mean that marginal conditions aren't optimal, but they may be acceptable to you. Whereas obviously IFR conditions for a VFR pilot, usually that's not an option. Same situation, of course, for an IFR pilot. If it's really, really bad, the conditions are below approach minimums, you're not going to go. But if the conditions are borderline, you're more likely to go, which once again requires us to do more homework and have better out options in those types of situations when things get tighter relative to our personal minimums. So one of the keys in benefiting a VFR pilot, and by the way, this is in fact actually a requirement in the ACS. It does actually require pilots to be able to estimate in-flight visibility. You don't usually see it tested, but it is still listed actually as a requirement according to the ACS. So if you're flying along and you've asked yourself, what's the visibility? If you haven't, the next time you're flying and you do ask yourself, what's the visibility? What are some ways you can estimate? In other words, as you're flying along, as you approach a warm front, maybe the forecast conditions were marginal or better, and yet it does look like the visibility is deteriorating. How can you estimate in-flight visibilities to A, affirm that in fact, yes, it is getting worse, but also B, of course, to give you some type of numerical estimate. You can't wait, and nor should you wait until you've got enough experience to where you can just kind of eyeball it. You can't even really explain it, but some pilots can kind of just say, I think it's this. I can't really tell you. I just have a gut feeling based off of previous experience. Instead, there's some methods there. So let's take a look at a couple of them. Some, of course, take less time, while others are better as far as their accuracy goes. And, of course, it depends on how well you execute. So let's just read these together. Some of the methods we can see. The first one, of course, pick the farthest landmark visible to you. And you're traveling towards, obviously, you've got to be traveling towards it, and measure the time that it took to travel to that checkpoint. And then, of course, multiply by your ground speed to figure out what it would be. So in association, this is an example. If you were doing, I don't know, 180 knots, which is about 3 miles a minute, and it took you 20 seconds to get to the point that you can see, then obviously you have 1 mile of visibility. Clearly that would be bad for VFR pilots, obviously. You probably already figured that out well before you got to that point. But the idea, of course, is that you're going to hopefully see farther than that. It's going to take you more than a minute or two to get to that point. Another method on the left-hand side there, you use a runway as a ruler. If you're flying past a runway, pull it up on ForeFlight. How long is that runway? And then in conjunction, if you need to, visualize the length of that runway out in front of you or even to the side to see how many miles of visibility you can estimate. That's another way to kind of give you a numerical estimate. On the bottom, while flying in proximity to an airport, evaluate the weather. This is kind of more of a practice thing. This is one thing that I'd recommend you do to develop experience, is just gauge what you think it is before you even listen to the weather. Create your own estimation. Just practicing based off of the 2 previous examples, perhaps maybe, or a combination of them. And then listen to the automation weather and compare. This will give you that ability to begin to gauge it just by eyeballing it. However, one of the main go-tos that I oftentimes use is a point of reference. Now, this won't give you the exact visibility unless, in fact, this is the only thing you can see. But imagine the only thing you can see is the ground directly visible above the nose or just beyond the nose. That ground that you see in front of you, for the average airplane, it's not an absolute, but for the average airplane, it depends on how far out your nose extends in front of you, admittedly. But for the average airplane, the general aviation airplane that you guys are probably flying, it's about the same distance as miles as the altitude of the airplane. So let me draw that out real quick. The idea basically is you have an angle created by the visible side over the nose. So if this is the nose of the airplane, and this is your eye line seat height, then of course you're able to see at an angle beyond the nose, and then of course the ground below you. And then what you're really doing is just some basic angular math that you're going to see a certain distance forward relevant to a certain distance above. And so for the average angle of most GA single engine piston airplanes comes to about 0.2. Now, I'm not going to go into the math. If you guys want to know this more, that's perfectly fine. I doubt anybody does. But the point is, if you do the math, what that really ends up being is if I'm at 1,000 feet, then that equates to being able to see ground directly visible over the nose as 1 nautical mile away. Now, this doesn't help, of course, if you can see ground further beyond just over the nose, but it still gives you a point of reference, so then you can still at least have something to give you an idea of what visibility you do see. Just as another example, therefore, if I'm at 8,000 feet, the ground I see directly over the nose is 8 miles away from me. Okay, why do we care again about these? Because again, just to reiterate, if we are flying into conditions that are deteriorating, the more apt we are in relation to determining visibilities, the better we're going to be able to immediately say, yeah, conditions are deteriorating. It's time to modify our route or get on the ground before things get too far out of hand. Get a drink of water real quick and we'll finish up. All right, one of the things I want to talk about, of course, is especially for those who have never done this before, maybe you've thought about it conceptually, but you haven't really applied it, is establishing your own personal minimums. 4 things I want you to think about when you try to do this, making sure that specifically before you go on a real flight scenario. So this is especially the key after you get your license for your VFR pilots or your private applicants. Perform this before you ever go into any flight scenario. This is specifically important because you don't want the E of the PAVE checklist acronym to be in any way, shape, or form an influence in your decision making. Meaning, there are oftentimes, of course, emotional reasons why we are going on these flights, and they will influence us. They've influenced lots of good pilots to make emotional decisions. You want to establish personal minimums in a situation where you're not being emotionally influenced. So do not create a personal minimums in conjunction with any specific flight. They need to be performed before that actual flight scenario. You need to be honest and realistic. And what do I mean by that? I mean, you need to be honest with yourself to say that, yes, I can actually follow these minimums. If you create excessively restrictive minimums, you may not follow these, and then doing this was kind of fruitless in the first place. You just maybe did it to check the box off because you were told to do it. So be honest with yourself and realistic that, yes, you can actually follow these personal minimums and use them for your benefit. Consider the dynamic of the plane and the pilot, meaning it's not just about you, it's also about your abilities with the airplane you're going to be flying, and also about the plane itself. I'll give you an extreme example. When you consider your personal minimums relative to an airplane, you also need to consider the abilities of the airplane relevant to the route of flight. If I was flying a Airbus A330 or an A380, a large transport category airplane from JFK to London Heathrow, it's not that big a deal. It's designed for that. If I was flying a Cessna 162 from JFK to London Heathrow, it's a lot bigger deal, right? In fact, because that airplane's not designed for that. And so I need to have a whole lot more know-how about that airplane. I need to know its ins and outs, its abilities, its limitations. Not to say that you wouldn't need to know that to be safe in the first place, but you get what I'm saying. You're going to have to do extra planning. You need to know that there's fuel in Greenland because you're obviously going to have to stop and get fuel. You're going to have to modify the airplane probably to get it across the North Atlantic, the risk factors involved, etc. So consider also when you think about personal minimums, think about the airplanes you're flying. Think about that element of well, I could fly to California in this airplane, but what am I going to need to do in relation to my own personal minimums? Am I going to fly there on my normal 5 hours of sleep, or do I really need to actually have, in these types of situations, 8 hours of sleep? And by the way, this is a living document, which means after you've gone on a flight, especially if you've gone on a flight, your first flight where the weather pushed you a little bit emotionally, where it created some unease, review these personal minimums post-flight to adjust them if necessary or modify them, sometimes more conservatively, sometimes actually to where, yeah, I handled that well. I think I can now move this number up, or etc. So again, you do this, when you create these personal minimums, it actually creates more flexibility, not less flexibility, to where we move away from just an absolute no-go into, okay, what types of things can I modify to make this risk involved in this flight more manageable? So before we end, I just want to show you a couple of examples, because it's one thing to talk about establishing personal minimums. It's another to actually do it. Everybody's different. Some people are more numerically influenced. Some people just kind of need some kind of point of reference. The point is, there are lots of ways to go about this. Yes, there's the PAVE acronym, but if you actually want to put something down on a piece of paper, let's take a look at a couple of examples. So with AOPA, they have something called a contract that you make with yourself, basically. This is a VFR pilot personal minimums contract. There's also an IFR one as well. So you agree that you will fly within your own established personal minimums. You can see that it does generally follow the PAVE aspect of the pilot, the aircraft, the environment, etc. So in this case, you can of course see that you establish how many minimum hours you will accept, how many minimum hours in type, things of that nature. For the airport, minimum runway length, minimum runway width. Aircraft, of course, what kind of fuel reserves are you going to accept? If it's a night flight, will you accept it in a single engine airplane or you're not? And then of course, if you are going to fly at night, what additional limitations will you establish for yourself? Will you fly at night in mountainous terrain or over open water, or in rural terrain for that matter, where there's not a whole lot of lighting on the ground, things of that nature. Weather-wise, you could go well beyond this, but at a minimum, maximum wind velocity and gust, crosswind, minimum ceiling, minimum visibility. Also notice that it doesn't just talk about personal minimums, it also talks about these are the types of things that I'll always do before I fly a specific type of airplane. So you can see, like for example, on the first one, only fly when I'm proficient with the aircraft limitations, performance, normal and emergency procedures, systems, and avionics. So this is one way to establish your own personal minimums. Another one that goes a bit even beyond establishing personal minimums is what we call a flight risk evaluation tool. I'll give you an example of one here. So this is where you establish a numerical valuation of risk. You think about risk in relationship to each individual section. It's kind of like the PAVE checklist, except now you're looking at each individual item and then you're valuing that risk based off of its severity relevant to you. So as an example, you can see if you're a captain with less than 200 hours in this type, then the risk value is 5. If you're single pilot, you're not even flying in a multi-crew situation, which would of course be all of us, and at least what we're talking about right now, then you can see that irrespective of your experience level, it's automatically a risk value of 5. So I would write down 5 there. On the next page, sorry, let's clean that up just real quick. On the next page, as you would imagine, it goes beyond just pilot experience. It goes into the environment also. So as another example, let's say, this is IFR stuff for you VFR pilots too. So bear that in mind, that depending on which one you use, it of course takes those types of things into consideration. So let's say, if, for example, for you IFR pilots, that they reported that they haven't been able to de-ice the runway. So the runway, of course, is contaminated. So you have an increased risk value there. Let's see, it's a night operation. So we've already got a risk value of 5. Maybe we were considering that B-52 report of severe turbulence. So another 5. And of course, you get the idea. You add your risk numbers together and you get a total value. Now, that total value is something that you have to think about in relationship beforehand, meaning you think about, okay, if I ever have a risk value over 18, then I'm either going to discontinue the planned flight, or I'm going to modify something, meaning instead of going to an airport that has a contaminated runway, or going to an airport that is anywhere near a report for severe turbulence, I'm going to change the plan, and therefore, of course, re-sum my numbers up, and I find my number is less than the tolerance of 18. So now it's an acceptable flight to me. These are some ways, of course, to pre-flight risk in relationship to your choices, and also helps you make a different decision. So you could see that I kind of just pulled out the idea of changing my route to the south, but consider the idea that before you even thought about that, you first looked at your original plan and evaluated the risk relevant based off of a tool like this. Now, this is not for everybody, right? Some people are probably like, oh my gosh, I can never imagine doing this. If it's not for you, then don't even consider doing it. But for those that you would think that this would be beneficial, these are just some examples. At a bare minimum, certainly as an expectation when it comes to the ACS, you definitely need to have a very basic recall tool to recognize where risk is. And in association, I would recommend that you use that when you're thinking about planning. So once again, you think about planning. Before you finish the planning, you've already evaluated your risk, and therefore that helps you perhaps reconsider your planning before you kind of commit to a particular route of flight. All right, that's about it for me. I know I said I'd let you guys go at 9 o'clock, so it's 9 o'clock. I will stick around, as I have said before, and hang out for about 5 minutes in case anyone has any questions. Otherwise, if not, you guys are free to go. Thank you so much for coming tonight. Ed will be, of course, back on next week with his second session on the flight portion of the practical. And then next Thursday, I'm going to have to move my session that was supposed to be on Wednesday to next Thursday. That will be on, it's either going to be on airworthiness, or I've had some input that we may end up moving it back to human factors on specifically spatial disorientation, all the illusions that create spatial disorientation. It will be between those two options once I get some more input from a couple of folks. So again, thanks for coming. Again, I'll stick around for 5 minutes or so. Answer any questions.
Evan, also on Wednesday night, Mac is doing aviation trivia, 7 p.m. Wednesday night.
8 p.m.
8 p.m.
8 p.m. on Wednesday. Yeah, trivia.
Okay, my correction. I just want to make sure it got plugged.
Yep, thank you.
Thanks, Evan. Appreciate it.
Got a question for you, Evan.
Sure.
Where did you find all of the math, geometry, whatnot for the estimating in-flight visibility?
So basically, it's just a tangent relationship. It's just Pythagorean theorem, really, is all it is. So if we pick some numbers, let's say that your eye line puts you 6 feet off the ground. So you're 6 feet vertically above the ground. And as you look out over the nose, you could even do this in an actual airplane. You could go sit in your airplane and you could look over the nose and you could find a spot on the tarmac. Maybe you're lucky enough that it's one of the T spots for the tie downs. And you get back out of the airplane and you measure the distance, which, would be easier said than done. But if you could do it, get at least within a foot, you probably get a pretty accurate estimate. Let's just say that number is 30. So all we're doing is we're just creating a ratio, right? So in this case, 6 over 30 would be, I just created those numbers, so I have no idea what that number is going to be, but let's see here. So that ended up being 0.2, actually. So now let's take that and then apply it in an in-flight scenario. So your angle now, right? So I know that my angle is 0.2. I know my altitude is 2,000 feet. So what I want to know, of course, is this number. So what I end up doing is I just end up taking a tangent of that value. Now, if you're familiar with tangent, that's fine. If you're not, it really doesn't matter. But the point is that ends up creating the ratio to determine the number. So let me just do this.
What are you trying to figure out?
Are you trying to show us on the screen?
Oh, you guys can't see anything. I'm sorry.
No. What are you trying to figure out? I don't understand.
Hold on. I fell out of my presentation, so I forgot completely to share the right screen. You guys are completely not seeing what I'm doing. All right, let me start over. Sorry about that. Thank you. You guys should have said something. I do that way too often. All right, so you're sitting in your airplane on the ground. Here's the nose of the airplane. Here's your eye line. You can see that spot. You know that you're 6 feet off the ground. And we were lucky enough that we found out that this was 30 feet by getting out of the airplane and measuring this. This is not something I recommend people doing. This is how this math was created. So you do 6 over 30 and you get your ratio of those two numbers, which is 0.2. So this angle creates a predictive value that if you know this number, you can figure out this number. And so in association—
Is that the Pythagorean theorem?
Yeah, exactly. That's all it is.
Okay,
So
and what do we use this for?
I'm not saying to use it at all, but he was asking how I came up with the math to say if you're at 1,000 feet here, how does it end up being about a mile horizontal distance? And so that's all I'm doing is just explaining to them how that math works. So if my angle was the tangent, was created a 0.2 value, then you can see that if I want to know 1,000 over x equals 0.2, then to solve for x, of course, I can, let's see.
Be 200, right?
No, it would be, here, I'll just do it by calculator. It's too late. Apparently I can't move my values over.
Sorry, is the 1,000 because you're at 1,000 feet?
Yep. Yeah, exactly. So if I was at 1,000 feet and I want to know what x as far as the distance goes is,
It's 200, right?
no, it's 5,000 feet.
Wait, what?
Mhm.
I thought you had to multiply. Where on earth did you get that from?
Well, I could do this a couple of different ways.
I thought you just had to like multiply both sides by 1,000, right? What? I don't understand why. Like, I missed something. I don't understand why, like, what's the, why?
So let's go back again.
Where in the presentation was this? Because I must have like missed something.
It was right here.
What is it in relation to is what I want to know. Like, what is it like?
When he was trying to tell you how to estimate how far you are away from clouds.
I can't hear somebody saying something.
So you see the orange box right here?
Yes. The ground directly visible beyond the nose of the airplane is this. Okay, and that's to estimate how many miles you can see?
Correct.
Oh, okay.
So, and then I was asked where that math comes from. So going back to this math, if I was
Okay, so it's not something that's like directly weather related. It's just estimating about how far away something is.
It's directly weather related in the relationship that if you see weather's deteriorating, you can affirm that relative to how your visibility is actually deteriorating. But more specifically, it's required in the ACS because the ACS requires the ability to estimate visibility. So this is just one method of doing that.
Oh, okay, visibility. Okay. I got you.
So decision-making wise, if you see your weather deteriorating, obviously you can affirm that in a number of different ways. As I said, this isn't an absolute number that's going to work every single time, because probably if you've waited until the visibility is so bad that all you can see is the ground directly over the nose, you've already made several bad decisions. But specifically with this one, what it is useful for, of course, is it gives you at least some point of reference, that you at least know that if you're at 5,000 feet, so do the Pythagorean theorem, if we're at 5,000 feet and we've got a 0.2
Can't
angle.
see your thing.
Yeah, let me switch back over.
Okay,
if
so
you're
that was just
5,000 feet,
okay.
then let's see, for 5,000 feet, you would be, that's 25,000 feet. So of course, if you convert that into miles, it's about 5 miles. So you can see that if you slice that off, this distance basically ends up being the same number in miles. So 5,000 equals 5 miles, 4,000 equals 4 miles, etc. Now, if you can see beyond that, great. But at least now you have a point of reference. Whereas most of the times, if you ask someone, how far can you see at 5,000 feet? They may have no clue. At least this gives them some point of reference to then at least I can see the ground over the nose and I can see well beyond that. So I've definitely got well beyond 5 miles of visibility. It's not a perfect technique, but it's better than having nothing at all. For most people, probably the best thing to do is to pick the landmark far away from the airplane and then measure the time it takes to get there, and that gives you an idea of visibility as far as your ground speed goes.
So you're saying 7th grade quick math is 1 mile for every 1,000 feet?
Yep. At least in this type of airplane. Obviously, if the nose is longer, your angle is going to be shallower, which means, in fact, you'd actually see further away from the airplane as far as the distance goes. But yes, generally, most of these GA airplanes come to an angle of about 0.2, 0.25, something like that. So therefore, you can use this adage of the ground is approximately the same distance miles as how high above the earth you are.
So my question is, where do you get that angle, the 0.2 or the 20 degrees?
I got it from some document I found forever ago. I'll have to look it up to even remember where it was. But basically, it's a small, old document that shows the idea and then shows different types of airplanes that have actually they've done this. So they've actually gotten out, I guess, on the ground and measured the distance. You could do this yourself, I guess, technically, if you wanted to, by getting in the airplane and measuring the number. Now, have I actually tested this? Like, for example, in a 172, yep, it works. Most aircraft that I've tested, as far as at least single-engine piston airplanes, hasn't been an issue. Multi-engine airplanes, especially the longer noses, it ends up being a bit off on the mass, so you've got to add a little bit more in that situation. So
yeah, that's just what I was wondering, was like if your eyes are at the seat height level, or like where that's stated or how that angle's figured.
yeah, again, it's not an absolute, but it's better than having nothing at all, which is what most people have.
Yeah, for sure. All right, Evan, thanks a lot.
Sure. I believe that was Kevin that asked the question about the math.
Yeah, that was Kevin.
Yep, thank you. Really appreciate that.
I have a question, Evan.
Yes, sir.
So the air circulating around a low, air moves from high pressure to low pressure. It's counterclockwise. Where does it all go when it gets to the middle?
Well, obviously it goes up in the atmosphere and then disperses outward. It also depends on what's happening above it, because for example, lots of times what I was talking about before with the 18,000 foot influence is some of the nastiest weather you can experience, like clear air turbulence, for example, in the mid levels, is where you have perhaps a closed low system above a surface low. And so that low air that's being spilled out, that low pressure air that's rising and spilling out from the top of the low pressure system at the surface is now in violent interaction with the closed low above it. Whereas other times, the low pressure system above it may in fact encourage that low pressure system to not only move in specific directions, but be able to maintain more stability in its auto rotation. So the answer to your question is it kind of depends. It depends on what's above the surface low in relationship to it. But generally, yes, the air is going to move into the upper altitudes in the upper atmosphere. That would be probably the best generalized statement.
And sometimes you hear during a hurricane that the hurricane has to breathe.
Mm-hmm.
And I think they talk about the outflow hundreds of miles away from the hurricane as part of the ability of it to breathe.
That would ultimately be that upper altitude shear, for example. So it is kind of, as far as what one system does as opposed to another, is going to depend on not only the system itself, but like you said, its surroundings. So generally, we just say the air moves into the upper atmosphere. What it does from there, like I said, is going to depend on what else is around it and what's above it. But yeah, that's probably a good point. I think I intended actually to talk about that a little bit more to make sure people understand that a surface low doesn't mean that that's happening uniformly. In fact, if I'm not mistaken, I did take some shots, but I don't think I saved them on here, just showing the different winds aloft. So do this on your own, of course, is look at the wind barbs across the country with this low pressure system at lower altitudes. And as, of course, you move into the higher altitudes, you will see that that surface low is not having any influence on the prevailing winds above it. And therefore, you can see, of course, the vertical limitations of that low pressure system. Generally starting somewhere around 18, 21, 25,000 feet, you start to see a dissipation, if not complete removal of that circular wind flow pattern and more of a prevailing westerly wind moving across the country. So that again, like we said, it's definitely going to steer the low, but it's also, of course, going to determine what the low does as far as intensify or weaken. You probably have heard of like you talked about with hurricanes, where we talk about shear aloft. Whether or not they're shear aloft or not, of course, helps break up a hurricane, or at least weaken it or keep it from getting too strong. That's all about that upper altitude exchange with the low pressure system and what's going on above it. So hope that answers your question. We'd have to get into like literally, I mean, I would have to pull up some of the old meteorology stuff to look at all the different examples of different situations can occur and how that influences stuff. Probably need to get a real meteorologist in for that, though.
Yeah, I was just thinking how I could help you determine what's going to happen to a low that's in the Midwest and what's going to happen to it by the time it gets to the East Coast.
Well, unfortunately, even the models don't do that good of a job. So predicting not only the pattern but also the intensification or the dissipation is a hard thing to do, I think. All right, anybody else have any questions before we head out? All right, well, again, everybody, thanks for coming. I will have this video to share in the next couple of days. If I don't run into any issues with the rendering like I did with the DPE recording from last night, but that is uploaded this evening, so I will send out an email in a little bit to share that. So you'll have that, and you'll have this one in the next couple of coming days.
Thanks, Evan.
Yes, sir.
Thank you.
All right, guys.
Thank you. Have a good night.
Bye now.